Alright, so in this video, we're going to move on and talking about specific heat capacity problems. In the last video, we just did some very basic specific heat capacity problems. In today's video, we're going to talk about two object problems, but before we get to that, I want to see a problem with power. Okay, and so take a look at example 3. Example 3 says a 1200 watt. As soon as you see watt, you should be thinking, wait, watt? watt, that's power, right? That's joules per second, right? 1200 joules per second. So this 1200 watt kettle takes 4 minutes to heat water from 15 degrees Celsius to 80 degrees Celsius. In your mind, you should be thinking, okay, so that's 1200 joules per second. It takes 4 minutes. So 4 times 60 is 240 seconds to heat water from 15 degrees Celsius to, so this is Ti, and then this is going to be Tf. And we're given the specific heat capacity of water, which is 4200. We're asked to calculate the mass of the water in the kettle. Now we know Q equals mc delta T, and we're looking for M. We don't have Q, but we have the power of the kettle. And if we make the assumption that, number one, the kettle is 100% efficient, which is not a good assumption, and number two, that all of the energy produced by the kettle goes into heating the water, which is also not necessarily a good assumption because some of it goes to the kettle itself. But if we make that assumption, then we can find Q by just doing 1200 watts, that is 1200 joules per second, times 240 seconds. Because remember, power is energy over time. And in this case, the energy is not like, mechanical energy, but it's thermal energy, it's heat. And so 1200 times 240 gives us 288,000 joules of heat. And so that is our Q in this problem. And then from here, it's a simple calculation because we're looking for M. We have 4200, and then delta T is going to be, final minus initial. That's going to be 80 minus 15. And so I can just do some basic math at this point. Okay, so I divide by 4200, I divide by 65, and I get 1.05 kilograms of water. Okay, and so that is it for example 3. Pause it there if you need to look at that some more. All right, so the main thing I want to talk about in this video is two object problems. Okay, and a two object problem is, well, exactly what it sounds like. It is a problem involving two objects exchanging heat between each other until they reach thermal equilibrium. Now, I do want to point out, so far, we've been doing problems with mc delta T. We've ignored the possibility of any phase changes. That's going to be coming next. And so for right now, we're going to focus on two object problems, and then later on, we'll learn about latent heat and phase change and all that stuff. Okay, and so the basic premise of a two-object problem is this. You have two objects somehow placed in thermal contact with each other. And we know from the notes from the first day that when you have two objects in thermal contact, heat is going to flow from hot to cold until they reach what's called thermal equilibrium. Okay, that is when they reach the same temperature and there's no more net heat flow between them. We're going to make the assumption, for simplicity, that 100% of the heat flowing out of the hot object is going to go into the cold object. Okay, so in other words, we're going to ignore for these two object problems the possibility of heat being lost to the surroundings or lost to, elsewhere. Okay, in other words, the heat flowing out of the hot object is equal to the heat flowing into the cold object. And the way that we write that, mathematically speaking, at least conceptually, is we write Qn, that is the heat going into the cold object, is equal to negative, or minus, the minus sign is important, Q out. That is Q out is the heat coming out of the hot object. The minus sign is just to make the numbers come out correct. Because remember, if you gain heat, you have a positive Q, and if you lose heat, you have a negative Q. And so in other words, I'm saying if you have two objects that are exchanging heat, the heat gained by one is equal to the heat lost by the other. And so the number is the same, but one is positive and one is negative, and that's why you have the minus sign in the equation to make that come out correct. Okay, so now how do you apply this equation? So for now, before we talk about latent heat, which we'll get to later, all we have as far as Q equations go is mc delta T. And so that means you can think of it like you have mc delta T on the left and you have mc delta T on the right. And it's two different equations because there's two different objects. Okay, now Qin, you're usually talking about the object that the heat is going into, and Q out, you're usually talking about the object that's losing heat. I will tell you though that if you get those two switched in this equation, it honestly doesn't make a difference. Okay, as long as you're consistent with everything, what you put for Q in and what you put for Q out isn't really going to change your answer for everything. Right, so don't lose sleep over that. But let's take a look at some examples so we know what we're looking at here. All right, so example 3. So example 3 says a 2 kilogram substance of an unknown metal is heated in a blast furnace to a temperature of 300 degrees Celsius. It is then removed from the furnace and placed in a very well insulated container holding 2.5 kilograms of liquid miracle tonic. And this liquid miracle tonic has a specific heat capacity of about 2000. And the miracle tonic has an initial temperature of 70 degrees Celsius. It says in the problem the system reaches a constant temperature of 90 degrees Celsius. Okay, so there's a lot to unpack here. Before I get to the actual question itself, let's do some labeling. All right, so I'm going to call this 2 kilograms. I'm going to say that is the mass of the metal. So I'm going to write mm. It doesn't really matter what you want to call it. You could call it M1, you could call it mass metal, you could call it MM, whatever. I'm going to call this is the initial temperature of the metal. Okay, this is the temperature of the metal at the beginning of the problem because after it's heated up, it's then placed into the miracle tonic. And so I'm going to call this Ti, that's the initial temperature of the metal. All right. It's then removed from the furnace, placed in a container holding 2.5 kilograms of liquid miracle tonic. So I'm going to call this mass, I don't know, MT for M tonic, I guess, with a specific heat capacity of 2000. Okay, so that's going to be CT. And that has an initial temperature of 70 degrees Celsius, so I'm going to call that TIT. Now look at the last sentence. The question or the sentence says the system reaches a constant temperature of 90 degrees Celsius. Now think about what that means based off of what we talked about in the past. These objects are going to exchange heat back and forth until they reach thermal equilibrium. So when it says the system reaches a constant temperature of 90 degrees Celsius, that's saying the final temperature is going to be 90 degrees Celsius both for the metal and for the miracle tonic. So they both have the same final temperature because they're going to reach thermal equilibrium. It's implied in the problem, right? Just like basically every two-object problem, it's implied. Now the first question says, how does the heat that flows out of the silver compare to the heat that flows into the water? All right, so try to answer that question on your own. All right, well, we just talked about this. We're going with the assumption that the heat flowing out of the hot object is equal to the heat flowing into the cold object. In other words, Q in equals minus Q out. That's the principle that we're going to use to solve this problem. All right, so what I'm going to do now is I'm going to take this equation, Q in equals minus Q out, and I'm going to expand it out using my Q equals MC delta T equation. So on the left side, the heat's going into the miracle tonic. And so on the left side, I'm going to write Q in, I'm going to write MT CT delta T T. And on the right side, Q out, I'm going to write minus, and then heat's coming out of the metal, so that's going to be the mass of the metal times the specific heat capacity of the metal times delta T of the metal. Now the question asked me to find the specific heat capacity of the metal, and it looks way worse than it is because most of these values I actually have. So MT is actually 2.5, CT is 2000, delta T, the final temperature is 90, So it's going to be 90 minus the initial temperature of the tonic, which was 70. And that's equal to minus, don't forget the minus sign, it's really, really important. The mass of the metal is 2. C of the metal is unknown. And then delta T of the metal, the final temperature is 90. The initial temperature of the metal is 300. Notice that this minus sign out front in the equation, right, it's minus Qi, is important because 90 minus 300 is going to end up being negative. And so I need those two negatives to cancel. Otherwise, you get a negative value for specific heat capacity, which is not possible. So from here, all I have to do is divide both sides by 2, divide both sides by 90 minus 300. I'm going to go ahead and type that into the calculator just to save time. So I'm going to do 2.5 times 2000 times, let's see, 20, and divide by 2, and divide by 210, and I get Cm is 238.1 joules per kilogram per Kelvin. Or I guess per degree Celsius here, same difference. Okay, and that is the answer to example 3. All right, pause there if you need to look at that some more. All right, so this is a basic two-object problem that you see here. Okay, most two-object problems have a similar format. You have a hot object and a cold object, and you put the hot object in the cold object, and you're asked to solve for something. Okay, by the way, in some physics textbooks, this type of problem is not called a two-object problem. This is what's called calorimetry. And calorimetry kind of has the word calorie in it, and calorie is a unit for energy. You might not have known that, but calorie is a unit for energy. That's the same calorie like when you go to, like, Jack in the Box and it says like how many calories on the menu. That's the same type of calorie, right? Calorie is a unit of energy. It's not the SI unit, but it's a unit of energy. And one reason, one way that they find the number of calories, let's say in a jumbo jack, is they take the food item and they put it in what's called a calorimeter. And basically, I'm simplifying, but basically what they do is they burn it, they burn the food, or they explode it or something in what's called a bomb calorimeter, and the heat that comes out of the food goes into some water, and then the temperature of the water raises up, and based off of the difference in temperature, they can figure out how much energy was released from the food, aka how many calories are in the jumbo jet, because then they can just convert joules to kilocalories, which is what we use in this country to measure energy in food. All right, so fun fact, this type of problem is also called calorimetry, and yeah, there you go. So let's do a few more examples with two-object problems. All right, so example 4. This is a little more straightforward. This says a small amount of cold water is poured into a cup of hot tea to cool it down. And just as I go through, I'll label these. I'll call this, let's say, mass of the cold water, MC, and it's hot tea, so let's call it MT. What you call it, I don't really care. It doesn't really matter. I just need to label it something. So this is the cold water, this is the tea. Assume the water and tea have the same specific heat capacity of about 4,200, and assume the initial temperatures of the water and tea are 2 degrees and 40 degrees respectively. We're asked to find the final temperature of the water-tea mixture. Okay, so this is going to be Ti for the cold water, so TIC, and this is going to be TIT for the initial temperature of the tea. All right, so what I want you to try to do is I want you to try to do example 4 on your own, answer the question, calculate the final temperature of the water-tea mixture. Okay, so we start with Q in equals minus Q out, and then we're going to expand this out. By the way, right now, the only equation we have for Q is MC delta T. When we add in latent heat in the next video, these problems are going to be more complicated. And so, for example, if you put a small piece of ice in a cup of hot tea, the calculations are slightly more complicated than what they are now, because if you put an ice cube, the ice cube has to melt, and then the melted ice cube has to temperature change as well. And so it is going to be a little more complicated when we add in latent heat in the next video. But for now, we don't have to worry about that. So Qn, heat is going into the cold water, right? Because heat goes from hot to cold. So I'm going to put the cold water stuff on the left. So I'm going to do M, mass of the cold water, C for the cold water, delta T for the cold water, and then equals negative Q out. That's going to be MT, C, T, delta T, T. And now it's just a matter of plugging values in. On the left, I have 0.02 times 4200 delta Tc. The final temperature is unknown, so that's going to be Tf. The initial temperature of the cold water is 2 degrees Celsius. So minus that, minus 0.45. Specific heat capacity is 4200. And then delta Tt is going to be T final minus 40 degrees. And from here, it's basically an algebra problem. The algebra here is a little more complicated because we have to kind of simplify and distribute. So I'm going to do 0.02 times 4200, which is 84. Okay, so I'm just going to simplify this down a little bit. TF minus 2 equals negative, I'm going to do 0.45 times 4200, which is negative 1890 times TF minus 4. Okay, I'm going to distribute out on both sides, both the left and the right, and I'm going to continue working up here. So 84 TF minus, let's see, 84 times 2 is 168, minus 168 equals negative 1890 TF plus, because negative times a negative is a positive, so I'm going to do 1890 times 4, and that's going to be plus 7460, and now I just need to kind of rearrange and get TF by itself, combine like terms and all that. So I'm going to do, let's say, 1890 plus 84, and so I get, let's see, 1974 TF, and then on the other side, I'm going to do just a little bit of math, and I'll tell you what the answer is. The answer you should get here, assuming I did this correct, is, and actually, before I tell you the answer, I accidentally forgot a 0 here. That should be minus 40. So let me just double check my work. So that should be 75,600. So now I gotta do that math again. I will say, when you're doing these problems, you can always check yourself to see if your answer makes sense. Okay, logically speaking, this is what you should get, 38.4 degrees Celsius. So let's think to see if this makes sense, right? I put ice in the tea, or not ice, I put cold water in the tea. I didn't put a lot of cold water though, and so it makes sense that the temperature of the tea should cool down, but maybe just like a little bit. The initial temperature was 40 degrees. The final is 38.4. That makes sense. Okay, and so I'm happy with my answer for example 4. That is correct. The answer I got before was 3.84. And so when I saw 3.84, I thought, wait, that doesn't make any sense because the tea started at 40 degrees. It cooled all the way down to like 4 degrees just because a little bit of cold water. That doesn't make any sense. So when you're doing these problems, try to think about what it is you're doing, because sometimes people don't think about what they're doing, and they make mistakes, which I get making mistakes, but you should be able to spot your own mistakes. There's nothing wrong with making mistakes, but you should be able to like look at what you put and recognize if something doesn't make sense. So for example, if you put a piece of ice in water and you find the final temperature is higher than the initial temperature, right? You did something wrong. Okay, so my point is, just think about what it is you're doing. All right, so that is it for example 4. Pause there if you need to look at that some more. All right, and I think with those two examples, I think you should have a really good understanding of how to approach worksheet number 3. we can do another one or two examples in class maybe, but for right now, you should be able to start thermal physics worksheet number 3. Now, it's really important that you keep up with your worksheets because these worksheets are going to keep building on themselves. And so the first ones, we're just dealing with specific heat capacity. Worksheet number 3 is dealing with two object problems. Worksheet number 4 deals with latent heat problems. And then you get to like two object problems with latent heat and specific heat capacity and putting everything together. Okay, and so it's really, really important that you keep up with your practice worksheets because we're building, everything is building on itself. And so if you don't do one worksheet, then the next worksheet is going to combine things and you're going to get lost. Okay, so make sure you're keeping up with all of your practice worksheets, just like you should always be doing anyway. Okay, so at this point, you should be able to go into Canvas and work on thermal physics worksheet number 3. All right, so as always, please let me know if you have any questions, and I'll see you guys in the next video.